and I'm going to actually just kind of present friction to you the way it would originally be done in a physics lecture if you'd never seen it before. But what I'm assuming is that because you've done this friction lab, this is going to tie together a lot better than it would than if I just presented this in the first place. So here's the situation. We have a box on a surface, and we're pulling it with a force F, and it's got mass M. Now we're going to actually we're gonna actually add something to this situation. We're going to say that this box is going at constant velocity. And let's be clear on what that means. Constant velocity means in a straight line and at constant speed. So that's what constant velocity actually means in this situation and in any situation. Whenever an object is moving at constant velocity, meaning in a straight line or at a constant speed, whenever an object is moving at constant velocity, that means it's moving in a straight line and at a constant speed. That's what I was trying to say. Now, let's go ahead and recall Newton's first law right now. What Newton's first law says is the following. An object at rest stays that way until an external force gets it moving. Now, one other thing. Once an object is moving, it stays in a straight line at a constant speed. If it doesn't, and what that means is it might slow down, speed up, or change direction. A net external force makes this happen. That's what's going on. Now, we have the situation of a block being pulled and it's moving in a straight line at a constant speed. So here's the strange part about this based on Newton's first law. If we accept Newton's first law as true, so this we got from the dry ice lab, this we know is true, and we're given this situation. So we have this block being pulled by a force F. What's happening is because the block is moving at a constant velocity, we are forced to conclude that that I'm going to write it this way. I'm going to write no net force acts on it. And this is a fancy physics way of saying all the forces cancel. Okay, that's the logical leap that you have to make from Newton's first law. So if you're confused by this, you're going to have to back up and watch this a few times, and you're going to have to go over your notes in the dry ice lab, and you're going to have to go over the notes in the friction lab. So you're going to have to do all three of those things. And if it still doesn't make sense even after that, you're going to have to come see me, and we're going to actually have to talk about this and kind of have you hash out your ideas. So this is something that's going to take some work to really understand if you're not getting it right away. And there's no way to get out of doing that work. Okay? So that's the kind of dedication it takes to get this stuff. Now, if all the forces cancel, let's actually draw all the forces that are acting on this object. So we remember from the dry ice lab that any time you see an object that seems to have a natural tendency to slow down, it's actually the friction force that's opposing its motion. So for this block, if we were to draw the forces, these are the forces we would draw. We would draw the normal on the mass due to the surface, the weight of the mass due to the earth. There'd be the force pulling it to the right, and there'd be the friction force pulling it to the left. And what we remember is, from previous discussions, the normal force completely balances the weight in this situation. if this were not true, let's just pretend if the normal were greater than the weight, the box would fly up into the air. If the weight were less than the normal, the box would actually crash through the surface. Now, the other fact is, and that actually people are okay with that because they say, oh, well, it's not moving up and it's not moving down. In the y direction, in the vertical plus y direction, it's not moving. So people are okay with the fact that the forces are balanced in this direction. Here's the weird part about this from Newton's first law. According to Newton's first law, since this moves at constant velocity, the very disagreeable conclusion we are forced to say is that the force applied to this exactly equals the friction. And the reason we know this is from the dry ice lab. If you remember, we had that piece of dry ice and it would slide on the table and it would just keep going and going and going. What we realized is no force is needed to keep it moving. So the natural tendency of objects is that if something's moving at a constant velocity, all the forces on it cancel out and it just coasts. So here, what we're saying is every instant the force moves at constant velocity. Now let's talk about what would happen if these forces were different. Suppose the force were bigger than the friction, the object would accelerate. If the force were less than the friction, the object would slow down. So this balance of forces keeps it coasting at exactly a fixed constant velocity. Now, what we did in the lab after establishing these facts is that we actually did an experiment to relate the friction to the normal force. And now you've done the lab, you've plotted the data, I'm going to just sort of summarize the results here. We wanted a relation, a mathematical relation between friction and normal force. And this is the conclusion we reached. We said there's two types of friction. There's kinetic friction, which means the object is moving, and there's static friction, which is an object standing still. And what we concluded was the kinetic friction force is proportional to the normal force on the object. So this is normal on the mass due to the surface. And we call that proportionality constant. We read this, it's called mu. That's the Greek letter. And it's called the coefficient of kinetic friction. And this is the slope of that graph that you actually got in lab. And then for static friction, it's a different kind of friction. We have mu static times normal on the mass due to the surface. This is the friction that acts on an object as it's standing still. And this is the maximum possible value of that friction just before it starts moving. What we also found in lab was that the kinetic friction is less than the static friction for an object. You personally may not have found it, but when we go through the average of all the different lab groups, almost everybody found that this was true. So we got these three formulas here that we used, which is really great. Now, what I want to do is take a look at one of the example problems in class that will lead us into the lab that we're going to do on the very last day of this week. All right. So this is a problem that we actually had in class, and what I want to do is just kind of show you now how all these equations we came up with in the lab relate to a specific problem. So you tried to do these in class, but what I want to kind of do is show a little discrepancy that's going to lead us to our next experiment that we're going to do next time. So the weight of the block is going to be weight of the mass due to the Earth. That's going to just be given by the formula mg. So that's going to be 4, because I get 4 kilograms here, times 9.8. And we're going to get 39.2 newtons. Now, if we draw a free body diagram here, we have the applied force, we're going to have a friction force, we have the normal force on the mass due to the surface, and the weight of the mass due to the Earth. And we want to know what the normal force is. Well, the normal force in this case is going to be exactly equal to the weight because these two forces balance. And again, that's some previous part of this video, we realized that if they didn't bounce, the block would either fall through the table or jump into the air. So that's going to be 39.2 newtons. Now is our chance to use our new formula. So we have the kinetic coefficient of friction here. And so to calculate the kinetic friction, we're going to get mu k times the normal force. So in other words, you can't always assume that these balance. Nothing in this problem told us that these forces were going to balance at all. We have to tell you that it's moving at constant velocity. And they don't tell us that in this problem. We're not told constant velocity in this problem, so we can't assume it. So we're going to go ahead and calculate that now, and that's going to be 0.2 times the normal force, which is 39.2. And so when we do that, times force, 18. And if I have this right, I'm getting 7.84 newtons. Let me just go ahead and check that. So, perfect. So, now let's go ahead and calculate the difference between the kinetic friction on the block and the applied force. So we have the applied force of 10.46 newtons, and the kinetic friction is equal to 7.84 newtons. So if we actually look at the difference of these forces, the applied force minus the kinetic friction is going to actually equal, when we get that number, that actually works out to 2.62 newtons. Now, what we're going to learn later on tomorrow is, we're going to learn this resultant force. This is what this is called. This is called the resultant force because it's the combination of what happens on the right and the left. This resultant force does something to the block. And I'll leave that to you to guess for now. I'm sure you have a guess, and I'll actually let that be one of the Google Docs questions. Now finally, it says what would the minimum value of the coefficient of static friction be for the block to remain motionless? We're going to say force static equals, or friction static equals mu static times the normal force. Now in this case, if we were applying this force and it were staying still, then this would be true because we would say that it's not moving at this force that we're applying. So we have 10.46 divided by 39.2 equals mu static. We're going to go ahead and calculate that. And we actually end up getting 0.27 for our coefficient of static friction. So this is a good introduction to the friction problems. Next week, I'll be posting solutions to all these problems, but I expect you to kind of look at this, know how to do this now. This is certainly the kind of thing I'd want to put on a quiz for Monday or Friday.